Now, if you and then the other kind of gradient, right, that you do is a kind of a second order, this one, a differencing, and that's called a Laplacian. So a Laplacian is like the symbol is a del square. Okay, that's how you indicate it, and this is like in 2D it's like dou square by dou x square plus dou square by say dou y square on whatever you are applying it. So for example, if I say del square f, right? So f is my image, and if I wanted to apply if I say that I'm applying a Laplacian, right, this is what it means. That means I'm doing this. Oh, square. And the filter, right, that discrete equivalent of this actually looks like this, minus 4, 1, or of course, right, I mean it depends, 1, 1, 1, 1. Sorry, is there a doubt somewhere? Okay. Now, one way to explain, I mean there are right, different ways to actually explain this, and one way is simply to use a Taylor series kind of thing. So what you can say is, if I had f of x plus h, of course, this is a discrete case, but first, let's take a continuous case. Then okay, we have f of x plus h into f dash of x plus h square by 2 into f double dash of x and so on. Then the other trick that you play is, do this f of x minus h. And there you have like f of x minus h into f dash of x plus h square by 2 into f2 dash of x and so on, and then we'll neglect these higher order terms, and then if you simply add these two, right, you will get like f of x plus h plus f of x minus h, right, is equal to 2 f of x and then plus h square f double dash of x. Or in a sense, the approximation for f double dash of x is f of x plus h minus 2 f of x plus f of x minus h by h square, right? And a discrete approximation, if you take your h to be 1, right, so then it looks like, when you wanted a horizontal kernel, right, then what you're looking at is something like this, right? You're looking at 1 minus 2 1, all else 0. And if you repeat this for y, right, for the other this one dimension, then you will get something like this, right? You'll get 1 minus 2 1, and then you will get zeros elsewhere, and now you have to add the 2. If you add the 2, then you will end up with 1 1 1 1 on the 4 corners, and then minus 4 in the middle. There are other approximations also, right? It's not like there's only one, but the most common approximation, right, is this. And one of the uses of actually a Laplacian is that, and it's also called a zero crossing this one, a detector. Okay, zero crossing a detector. And this we will encounter, okay, this zero crossing and all is something that we will be certainly interested in. So for example, think of, say normally, right, your edges are not like, see, seldom will you find an edge like that, okay, in an image. It just jumps up, suddenly from 0 to 255. Okay, what is normally common is something like that. I mean, you have a gradient, and then it eventually becomes like 0 to 255. So it's normally hard to pin down, right, where the edge location should be. Right. So for example, if you had to say f of x like this, okay, then what you can do is, if you do and say f dash of x, right, then what happens? Then we have then we will have something like that, right? I mean, we'll have an increase, and then finally, right, it would kind of goes down to 0, always increasing. Therefore, it's always on the positive side. Then now, if you try f2 dash of x, right, what will happen? If we tried f2 dash of x on this signal, on let's say f dash, if we take a derivative of that, then it's like right, it's like initially climbing, and then right, eventually hitting a 0, and then the signal is actually falling, right, f dash, so it goes right negative. Yeah, so right, so you can think of something like that, right? So at 0, right, it will cross the 0, it will change its sign, and then it kind of goes on to the other side. Now this is a zero crossing, right, and the zero crossing is actually is an important information, provided it is also accompanied by kind of examining what is happening, what is the value of f dash of x, because I mean, if I just give you a uniform image, right, I mean, you'll also have zeros everywhere. So it doesn't mean that just because you have a zero, right, for the Laplacian, it doesn't mean that that's a very interesting point. You will get zeros even when you have a homogeneous image. See, one of the things that you must have observed is that whereas an averager always sums to 1, the weights of a difference will always sum to 0. You saw, no, like 1, 2, minus 1, 2, 1, minus 1, minus 2, minus 1, sum to 0, 1, 1, 1, 1, minus 4 in the middle, sums to 0, right. That is all because it is supposed to, they are all supposed to flag activity. This, when you have a difference, right, it's like, you want to kind of, find out activity, where there is some activity. And activity typically is in terms of a gradient, right, and that's why we call them as gradient operators. So if there is no activity in an image, right, it's like a smooth wall and you go apply a Laplacian, what will you get? You will get zeros everywhere, right, but that's not a zero crossing, right. So when you have a zero crossing, you can directly probably go and find out where the zero crossing is, or if you find that, Laplacian is ending up to be 0, you can go and find out with respect to dash of x what is going on, and that way, right, you will know whether it's an important point or not, okay. And typically a Laplacian is not actually used as a standalone because it's very sensitive to noise. I mean, the first derivative itself is sensitive to noise. Doing a second derivative makes it even more sensitive to noise, and therefore what one does is, one uses what is called a log, which is a Laplacian of the Gaussian. Okay, so this is called Laplacian of the Gaussian. And then right, given that this is all a commutative operation, just as in 1D, right, I mean H1 convolved with H2 is the same as H2 convolved with H1 and so on, right. So here also right, I mean here also if you see, right, what you can say is, you can say that I want to apply del square, right, my Laplacian, but then I'm not going to apply it directly on the image because then it makes it very noisy. So if my image is f, then I'll actually convolve with actually a Gaussian. So G is a Gaussian, and after I convolve, that's like smoothing it out a little bit. That's like low pass filtering it, and then I would apply a Laplacian, because that way I keep the noise under control. But this is also the same as, right, I mean, this is all straightforward, right, for you to show that this is also the same as f convolved with the same, right, del square of G, and this is a convolution, right. So all of that will go through. So in a sense, right, this is an operator by itself, just like del square is a Laplacian, del square G, where G is a Gaussian, is a kind of Laplacian of the Gaussian, and this goes by a particular name. What is that? Laplace, it has a particular shape which you have seen in movies. Mexican hat. So if you plot it, right, it will look like a Mexican hat. Okay, and no, it's again in the Fourier domain and all, right. You can, what kind of a filter do you think it is? If you have not attended my class before, I mean, otherwise you would know it, but somebody, right, from the rest, if you have not heard me before, what kind of a function do you think this must be in the Fourier domain? After all, right, you can examine it, the Fourier domain. What do you think it might be like? Anybody? A delta, I mean, sorry, a d by dt, if you do, what do you get? I mean, if I have f of t, it has, let's say, f of j omega, 1d, right? If I do d by dt, what happens? J omega, f of j omega, right? That's what you get. So d square by dt square, second derivative, minus omega square. So now can you tell me what is that kind of a signal if it's a Gaussian? Minus omega square, and then g of omega is a Gaussian, right? So in 1D itself, what will it be? Let's forget about 2D and all. Omega square e raised to minus omega square by 2 into sigma square. What is that? What will it be? What kind of filter will that be? At omega equal to 0? At omega very high? 0. So what kind of filter is that? A bandpass. So it's a bandpass filter, right? Okay, I think we'll stop here. I sort of exceeded the time.